Folks, I'm asking a question. Can you see my writing pad?
Yes, sir.
Thank you. All right. Today I want to talk about Laplace transform. All right. You see all these latecomers now? You know why they're coming in late now? Because they just handed in. They just turned in the homework, the test. I think in the future, I'm going to have to make it an hour before class time. I mean, it's really sad I have to do that. I want to talk about the Z transform. I hope you remember the Laplace transform. We have a signal x of t, Laplace of x of t. What do we call Laplace of x of t? What's that called? What's the name we give it? Nobody can remember what we call the Laplace of x of t? Wow. What's the point of us teaching you anything? Call it capital X of S. Capital X of S. The time domain is lowercase. And it's my friend, Mr. Johnson here. Mr. Johnson.
Yes, sir.
You see the importance of lowercase and uppercase?
To differentiate.
You see the time, excuse me?
So you'll be able to differentiate.
The lowercase is time domain, the uppercase is Laplace domain. This is uppercase. Okay. Similarly, we write x of t is inverse Laplace of x of s. Okay. And also to begin with, x of s is by definition the integral from 0 to infinity of x of t e to the minus st dt. Let's review. Let's review of 320 and 420. Okay. You had Laplace transforms in 320, and you had it in 420. Now today we want to define the Z transform. So
hold on, what is
say automatic control theory. If you don't know what it is, then you probably haven't done it yet. You're probably doing spring. Okay. So we write x of z is the Z transform of x of n. All right, so instead of writing S, we write Z. Okay. Again, this is lowercase. And this is uppercase. Give me a second here. Let me see who's with us. missing Mr. Kerr, but that's no surprise there. Okay. So Laplace is in the S domain. S domain. Okay. The Z transform is going to be in the Z domain. Z domain. And so we also have that x of n is the inverse Z, the inverse Z transform of x of Z. Okay. So this works just like Laplace transform, but of course, you're having trouble remembering Laplace transform. Right. And then the definition, x of z, is a sum, not an integral, a sum from n equals 0 to infinity of x of n times z to the minus n. That's the definition. That's the definition. Any questions so far? Okay, I'm going to a new slide. So if x of n equals delta of n, what is x of z? In other words, what is the z transform? What is the z transform of delta of n? Okay. What was Laplace? What was Laplace of delta of t? What was Laplace?
Unit, no, not a unit step function. 1, 1, 1.
Just one. Just one. So for the digital, the z transform is, let's apply the rule. What's the rule? The rule is, okay, x of 0, z to negative 0 plus x of 1. Okay, x of 1, z to negative 1 plus x of 2, z to negative 2 plus x of 3, z to negative 3 plus x of 4, z to negative 4, etc., all the way up to infinity. Okay. What can you tell me about x1, x2, x3, x4? What can you tell me about those? Wow. What is the value of x of 1 if x of n is delta of n?
All of x is 0.
0, 0, 0, 0, 0. And x of 1, x of 0 is 1. So we have 1 times z to the negative 0, which is 1 times 1, which is 1. So x of z then, if x of n equals delta of n, x of z equals 1. This is your first transform. There's your first transform. And you see it's the same thing in the blast. Any questions about that? Okay. That's then be a delayed impulse. Then X of Z
Thought I got it.
is, yes?
Thought I got it.
Yes.
You moving the paper so quick and you weren't saying nothing. I didn't even know you was finished writing on the last page.
Well, I said something the first time on the first page.
Nope. You just moved the first page too.
I don't think so. I'm pretty sure I said I'm moving the paper now.
Well, just now you sure you didn't do that for sure, and that paper wasn't even full, so I didn't even expect you to move it.
All right, I will replace page 2 because I may not have done for page 2.
Thank you.
Okay, got it? Mr. Pintod, do you have it?
Yes, sir. Anyway, body go.
All right. So this will be delta of -1, zeta -1, plus delta of 0, zeta -1, plus delta of 1, zeta -2, plus delta of 2, zeta -3. And again, that's 0, that's 0, that's 0, and that's 1. 1 times zeta -1, or just z to the power of -1. So if x of n equals delta of n minus 1, a delayed impulse x of z, this is z to -1. So now you know why I use z to -1 to indicate a delay of 1. Last class, I just told you, where you see delay, just put this. Now you know if you delay an impulse by 1, you delay an impulse by 1, the z transform is z to -1. If you delay an impulse by k, delta of n minus k, then x of z is z to the -k. Any questions about that? Okay, go on to the next page.
Got right.
Yes?
Could you explain to me why those at X is Z, all of them went to 0. Those 3 went to 0, but that one didn't. I didn't quite grasp that.
Come on. What is the value? What is the value of delta of -1? What is the value of delta of -1?
I sure.
Well, that's your problem. Here we are at midterm, and this is something I taught you about the second or third week. Delta of n, how many values does delta of n have?
Infinite.
No. How many values of delta? I didn't say n. I said delta of n. How many values does delta of n have?
1.
It has 2 values. What are those 2 values?
1 and 0. Sorry.
1 and 0. 1 and 0. When is it 1?
At 0.
When X.
At 0.
Yeah.
This is the only place where it's 1. Everywhere else is 0. So this is a question of understanding. This is a question of knowledge. What does that function look like? I defined that function a long time ago. As a matter of fact, I defined that function way back in 320. Does that answer your question, Mr. Johnson?
Yes, sir.
All right. I'm going to the next page. Or x of n equals u of n. What is z transform u of n? What do I mean by u of n, Mr. Johnson? What do I mean by u of n?
I'm too sure I think about the unit step function.
Mr. Johnson, why don't you know these basic things? It is the unit step function.
Yes, sir.
Why is there any question? So z transform then is by definition z of x of n is by definition x of 0, z to negative 0 plus x of 1, z to negative 1 plus x of 2, z to negative 2 plus x of 3, z to negative 3 all the way up to infinity. What's x of 0?
That's 1.
What's x of 1?
Everything is 1.
Everything is 1. Exactly. So what do we have here then? 1 plus
1 plus z to the minus 1.
plus z to the negative 2 plus z to the negative 3 plus z to the negative 4 all the way up to infinity. And if you know your math, you know this series converges to 1 minus z to the negative 1 divided by 1 minus z to the negative 1. You learned that in calculus when you do sequences. Or we can rewrite that as multiplied through by z. This is z transform of the unit step function. This is z transform of the unit step function. So z of u of n equals Z over Z minus 1. Now, I don't intend to get you deriving transforms, Z transforms, because we're not math students. We want to use Z transforms without having to worry about how they're derived. However, you must learn these. There it is. Okay. See this table? This is table 6.1. Table 6.1. You must learn table 6.1. The Z transform of the impulse function is 1. The Z transform of the step function is Z over Z minus 1. If you multiply the step function, actually all of these are multiplied by the step function. The Z transform of beta to the power of n. This is just this is a general case of one up here. Where we had 1, we replaced it with beta. This one up here is just beta equal to 1. This one here, this is just a ramp. That's Z over Z minus 1 all squared. Cosine is this one. Sine is this one. Decaying cosine is this one. And decaying sine wave is this one. You must learn these transforms because we will be using them all the time.
By the midterm?
Yes. By next class. And if you look carefully, it's not that much difference between them. Once you know the cosine, that easily generalizes to this, except that you have to insert beta. Okay. So once you got cosine and sine memorized, you got these two virtually memorized. So instead of it being 1, it's beta squared. And this one you got memorized. I mean, you must have this one memorized already. You just have function Z over Z minus 1. And then if it's not 1 to the power of n, it is beta to the power of n. Where you see 1, you put beta. Over here on the right-hand side is what's called a region of convergence. This Z over Z minus 1, I told you that came from the summation of that series. That's only valid if the magnitude of Z is greater than 1. But I won't be worried too much about the region of convergence of these transforms, because that really doesn't affect us too much in what we have to do. Okay. So you have your work cut out for you. Just like you had to learn Laplace transforms, certain Laplace transforms. These, by the way, these are the same time domain waveforms that you had to memorize for Laplace. The alternative is to make you derive them. All right. Give me a second here. You go back. Got away. I don't know why it's occurring. Okay. I'm going to switch page 4. let me go back and tell you that's something that you should know intuitively. The transform of 2u of n there should be no surprise when we can bring out the 2 times z of u of n. So that's 2 times z minus 1. Okay. So what all this is saying is if the time domain waveform increases by 2, the transform increases by 2 also. Or any constant. Another thing I want to tell you is what do you think the z of a sum is? What do you think the z of a sum is? What do you think the z transform of a sum is?
The answer should be a sum also.
Yes, the sum of the z's. So this should be z of 3 u of n plus z of 4 delta of n. Okay. We could bring the 3 out. Don't forget the brackets. We can bring the 4 out. And that's 3 times z over z minus 1 plus 4 times
1.
What 4 times 1? Yes. And we could leave it there. So that's 3 z over z minus 1 plus 4. Okay. Any questions about that? So it works just like Laplace transform. And of course, if this is negative, this would be negative instead. Okay, I'm changing slide 5. If you don't get it, just let me know, but let me know right away. Okay. Okay. Hey, my book is pulled apart. Let's do an example. Here's a waveform. Two, 0, 1, 2, x of n. 1 is 0.5. What's x of z? X of z is the z transform of 2 delta of n plus delta of n minus 1 plus 0.5 delta of n minus 2. Okay. So that is 2z of delta of n. Oh, okay. Got to tell you. No, we did that already. I forgot. Z of delta of n minus 1 plus 0.5 z delta of n minus 2. So clearly that is what? That is 2 times 1 plus what? Z to negative 1 plus 0.5 z to negative 2. Or simply 2 plus z to negative 1 plus 0.5 z to negative 2. That's the z transform of the top signal. Oh, by the way, 2 or 3 of you did this. When you're writing the code, why are you calling output signal X? Why are you doing that? I clearly define the input signal as being X. Why are you calling an output signal X? Once I've named something, you're not free to name something else. And if you plot in the output, then you can't call that X. That is Y. And the other thing I want to say is, I am amazed how little you students read. I send email after email about what not to do, and what do I get in the next half hour? The very thing I said not to do. In the future, I'm just going to mark it wrong. I'm not going to tell you how to correct your errors. Read the question. Nowhere in the question did I say, plot the impulse response. Yet 4 people, I believe it was 4, anyway, a high percentage of class, gave me the impulse response. I didn't ask for the impulse response. I asked for the output, and I gave you input in the question. So the output I was asking for is with the input I gave you. Before I go to the next page, any other questions?
Oh, the guy right in the impulse response is the output though.
But I'm not asking for the output when the input is impulse. The impulse response is the output only when the input is an impulse.
So the graph's supposed to look like a impulse graph?
No.
Supposed to look like an impulse response graph?
No. I don't know what you mean by that. Does look on the page. Does this look like an impulse response?
No. It looks like an input.
Yes, it does look like an impulse response, but it is not an impulse. So I'm not talking about the shape, I'm talking about what you're plotting. Impulse response. And I didn't ask for the impulse response. And I made that clear. I made that clear in 2 separate emails to you.
And the impulse response was given?
Yes, it was given, but nowhere did it say plot it. Where in the question did it say plot it?
So we were supposed to find the output signal through the input signal.
By using the filter command.
Exactly. Y'all just don't read. Y'all just don't read.
Like substituting like zero, like Y0 and stuff like that through the input signal.
I don't know what that means. You're supposed to use a filter command. You're supposed to tell the filter what X is, what the input is, and the input is not an impulse. I gave you the impulse, the input. Because I give you the impulse response, don't mean I want you to plot it. There's only one reason why I gave you the impulse response. So you can do part 5 of the question.
The input was for the part 4.
Yes. And this is another thing. I clearly said how to label those two M files. I clearly said that. And at least one person decided he's going to make up his own damn name. This isn't a 400 level class. Students not being in instructions. All right. Everybody got page 6? The only way you would know this graph on this page is impulse response is if you label it. Or this is the output you get when the input has an impulse on it. This is not impulse response. This is just the input. X of n. And of course, if there's an X of n, there's a Y of n. So there's a Z transform for the Y. And there's a Z transform for the H. The Z, what's the Z transform? What's the Z transform for the impulse response called? Let me see if you remember that. What's that called? From 320, what's that called? What's the class of the impulse response called? The class of the impulse response is called a transfer function. The transfer function, and the same is true. The same is true in the H domain and in the Z domain. It's H of Z, and H of Z becomes the transfer function. If you all had only learned 320 with a view to knowing it long term, this course would be a breeze. All of the concepts are the same. Well, not all. Many of the concepts are the same. Once you get past quantization and sampling, the concepts that remain are the same. All right. By the way, I'm not just putting this down here for my knowledge. This is a fact you must know. You must memorize. When you take the Z transform of the impulse response, you get the transfer function. Just like in 320, the transfer function was h of s. This is h of n is the inverse z of the transfer function. Both those statements are equivalent. You give me the impulse response here, I give you the transfer function. I give you the transfer function, you give me the impulse response. You look on last year's midterm, you see transfer functions there. Okay. Speaking of transfer functions, let's go there. Let's see if there's anything else I want to do here. Okay. One thing I have to do before we get there. So I'm done with page 6, slide 6, 7 now.
But Dr. Godray,
Yes.
I did the midterm and I remember seeing no transfer function on that.
Maybe I sent wrong. Well, not that wrong. Maybe I took that question out later. But we're doing it in time this year, so it could be there. I have to tell you one more bit of information. What I told you was so in the time domain, if we delay an impulse, then the Z transform would be Z to the negative K. Okay. Well, this is true. This is true of any signal. Z of X of n minus K. We delay an input by K. Okay. Then what's the output? What's the Z transform going to be? Z to negative K times X of Z, where this X of Z is the Z transform of the undelayed. This X of Z is simply Z of H of N, not H, X of N. X of N. In other words, when we delay a signal, what do we do in the Z transform in the Z domain? We simply multiply the Z transform by Z to negative K. We got something similar in Laplace. Laplace of f of t minus a was f of s. What's that? That's Laplace of f of t times e to the minus as. A similar kind of thing. Where to be consistent, let's call that k. Let's call that k. Here's Laplace of the original, and here's to indicate there's a delay. There's a delay. Here's the Z transform of the original, X of n, and here's the multiplier to indicate the original signal is actually delayed by K. Okay. Now we're ready. Now we're ready to talk about transfer functions. Remind me, in Laplace, what's a transfer function equal to? In Laplace, what's the transfer function equal to?
E of S over H of S.
Say again, please.
It ain't G of S over H of S.
I don't know what G is and what H is.
Oh, I know the output over the input.
Oh, what are we calling the output, Mr. Pintard?
I can't remember. I think it's G of S.
No. Right now, what are we calling the output? In this course, what have we been calling the output?
Why?
Y van.
And the input's X.
Right.
So the answer I was expecting from you was H of S equals Y of S over X of S. Okay. Guess what? It's the same thing. H of Z equals Y of Z over X of Z. X of Z. Same thing. So again, if you learn 320 really well, there ain't no surprises. Well, that's not quite true. There are not many surprises left in terms of basic theory. Well, let's get to it. How am I going to find Y of Z and X of Z? Well, what do we know? We start with a difference equation. We start with A0 Y of n plus, I'm just going to do a few. A1 Y of n minus 1 plus A2 Y of n minus 2 equals X of n B0 plus B1 X of n minus 1 plus B2 X of n minus 2. Okay, there's our difference equation. Difference equation. Now let's take the plus. Let's take the Z transform. This becomes A Y of Z plus A1 Z to the negative 1 Y of Z plus A2 Z to the negative 2 Y of Z. Isn't it? Because the Z transform of Y is just Y of Z. And we need this because we delay by 1. We need this because we delay by 2. Similarly, this is B0 X of Z. This is B1 Z to negative 1 X of Z plus B2 Z to negative 2 X of Z. Okay. I'm going to the next slide. We have A0 plus A1 to the negative 1 plus A2 z to the negative 2. Y of z equals B0 plus B1 z to the negative 1 plus B2 z to the negative 2 times x of z, or y of z over x of z. It's B0 plus B1 z to the negative 1 plus B2 z to the negative 2 over A0 plus A1z the negative 1, z, the negative 2. This is the transfer function. That's the transfer function. And we can multiply top and bottom by z squared. This becomes b0 z squared plus b1z plus b2 over a0 z squared plus a1z plus a2. And then we can divide by a0, top and bottom, b0 over a0, z squared plus b1 over a0, z plus b2 over a0 over z squared plus a1 over a0 z plus a2 over a0. This form here is called standard form. Standard form. And it's standard form because it's power of z, not z to the negative 1, z to the negative 2. And not only that, this coefficient right here on the denominator, the highest coefficient of the denominator is 1. And that's called standard form of the transfer function. Okay, let's do an example. I'm going to page 9. All right, let's do okay, this example. All right. Let's find the transfer function for this filter. Tell me what to do.
You could write out h of z.
Say again, please.
You could start by writing out h of z equals y of z over x of z.
No, we're not there yet.
I mean, the first thing I would do is write this on standard form of a different equation by moving the y's to the next side. Help me see it better.
You can do that. Oh, give it to me.
Y of n minus 4y of n minus 1
Yes.
minus 3y of n minus 2.
Yes.
Equal
And
X
yes.
of n equals x of n plus 0.5 x of n minus 1 plus 3x
Equals what?
xn.
Okay. So that's the difference equation in the normal form. So now what?
Can you find the z transform for each one of those terms?
Now what? All right. What does y of n become? What does y of n become?
Will it become y of z?
Y of z. What's the second term become? What does the second term become?
Minus 4z to the negative 1.
Or would
That's
it?
it?
Okay, I think you're lagging a bit.
Then it'd be minus 3z to the negative 2.
No. We didn't finish. We haven't finished the second term yet.
Then it'd be times y of z and y of z.
You have. That's y of z. Yes. Thank you.
Then the
And
next
the
term
third term.
minus 3z to the power negative 2 times y of z.
Yes. Now what?
Equal x of z You there, me, Dr. Cartwright?
X is Z. X is Z.
Or you like it? I say
You're
X and
breaking
Z.
plus 0.5 x is z
No, no, no. You
power
gotta say
negative.
you gotta say Z to the -1.
Oh, so you don't do that. Okay.
Yeah, should just let me down a little bit.
I was gonna put the z
Nah, what I talking about all the while, I show you with delta 0 and delta 1. When I show you Friday, nah, you don't forget it.
I had a rough morning. That assignment.
What y'all think y'all doing that test, boy?
You ain't gonna delta operates in the grids.
I think I do good.
You don't have to look
Boy,
at
that
it.
test was hell for me, bro.
But y'all start too late.
Oh, where I started from Masi Saturday, boy. It's just the octave I was in Tim doing, boy. The T block doing. But the rest I already finished, boy. Just the octave, boy. I ain't have octave on my computer. You see my computer mess up.
All right.
You ready now?
Okay. Who do they lose? So Pintard and Kerr. Okay. Somebody needs to call Mr. Pintard and tell him he has to sign his device on again. Okay. All right. 0.5 times what?
is it z to the minus 1 x of z?
Yes. What's the next one?
Plus 3z to the minus 2 x of z.
Now what? Now what?
We already know how to put them as a fraction. So,
Oh, we ain't ready for a fraction yet. We have to group like terms. Okay, now what? Now what?
and it's y of z over x of z.
Yes? Equal to what? And then this is the transfer function. That's the transfer function. Equals what?
So the goal is to get the transfer function.
Yes.
Equals just 1 plus 0.5 z to negative 1 plus 3z to negative 2 over 1 minus 4z to the power negative 1 minus 3z to the power negative 2.
And now how are we going to put this in standard form? How are we going to put that in standard form?
Remember, for the last example, you multiply top and bottom by z squared or something like that.
Yes, because I want to get rid of the lowest z to the negative 2. If that was z negative 3, then I'm going to multiply by z cubed. So this is z squared plus 0.5z plus 3 over z squared minus 4z minus 3. So this is now in standard form because this coefficient here is 1. Yeah. Are we clear on how we get the transfer function of a filter when you know the difference equation?
Dr. Cadre, so we cancel out those z minus 2s or something like that? Oh, we did for the standard form.
I multiply the top and bottom by the same thing. I multiply the numerator and the denominator by the same thing. What was that same thing? What did I multiply by? Young man, what did I multiply by?
Not sure.
Really? So how does 1 become this?
So you multiply by z, z2,
Z squared.
z squared.
That's not Z2. That's Z to the power of 2. Z squared. If I multiply Z to the negative 1 by Z squared, what do I get?
Just z.
Okay, and I multiply Z to the negative 2 by Z squared, what do I get?
Yeah, nothing actually. Just
No, I get 1. I don't get nothing. I get 1. Because I get Z to 0. And Z to the power of 0 is 1. I'll do the same thing for the denominator. Okay. Any other questions? Same problem. Same problem. Find the zeros of H of Z. How do I find the zeros of H of Z? Same H of Z. What do I mean by the zeros?
this is zeros in the denominator. Or
No, zeros is where the function becomes 0. That can only happen if the numerator becomes 0. If the denominator becomes 0, then you don't have a 0. You have a pole.
yeah, I got a mix up.
So that's when the numerator is 0, so Z squared plus 0.5 Z plus 3 equals 0. How do we solve that?
Quadratic one.
So how do you solve that?
Put it in my calculator. You need the formula, the quadratic formula.
So give me the solution.
It'll be Z equal, if you want to put it like that. You can put -1. No, 0.5 plus or minus.
Negative 0.5, yes.
Plus or minus open bracket. Square root 0.5 squared minus 4 . So you could just put -4 times 3 because the thing is 1. All that over 2.
What's the numerator equal to?
I get 3.
You get 3?
Oh, no, they're wrong. Square root of 3. I have this.
Is that a 12 in the numerator? The square root of 0.25 minus 12?
And how did I get 12, Mr. Johnson?
Not sure.
Look at the line right above it. How did I get 12? You don't see the 4 times 3?
Oh, no, so I thought that was a 1. 415.
And you thought that was a 1 because you don't know the quadratic formula? If you do the quadratic formula, there's no questioning of what that is. Again, you're copying down without thinking about what you're copying down. You're not doing yourself any favors by doing that, by the way. If that's what you're going to do, if you're just going to copy down without thinking about what you're copying down, you might as well just snip it. What's this equal to? What's that numerator equal to?
And I have to do some with I because that's a negative number inside the square root.
Square root of J, not I. We're electrical engineers. We're not mathematicians. J. What's that number equal to?
11.75.
Really? What happened to the square root sign? .428 divided by 2. Negative 0.25 plus J 1.714 or negative 0.25 minus J 1.714. Okay. This here is the first 0. And this here is the second 0. Okay. Therefore, we could write the numerator as C minus Z1 or Z minus Z2 divided by Z minus P1, Z minus P2. So this top is Z plus 0.25 minus J 1.714 and Z plus 0.25 plus J 1.714. Okay. So zeros are complex conjugates. Zeros are complex conjugates for this filter. I'm going to find the poles.
Poles, you have to deal with the denominator.
What specifically about the denominator? What specifically about the denominator?
Do we have to equals? Do we have to do equation for that equal to 0 also or no?
Yes, the poles are where the z values go to 0 in the denominator. So we're gonna have to find those. So this is z minus pole 1, z minus pole 2. All right. I'm going to the next page.
Hold on, let me get that. Let me get that. Let me get it now.
All right. Again, we did all this in 320. 0, so z is equal to 4 plus or minus 16 minus 4 times negative 3 all over 2, right, which is 4 plus or minus 16 plus 12, 28 over 2, which is 2 plus or minus 2.646. The one pole is negative. No, the other pole okay. We go back up here on the previous page. Previous page.
We need the formula now, right?
You need what?
I'm asking, do we need the formula now to implement this in the first one we's doing?
I'm not quite sure I know what you're asking.
The formula we had z minus z1.
Yes, I need the previous page. You need to go back here. You need to go back here. So I'm going to rewrite out the numerator. And then the denominator becomes z plus 0.646 multiplied by z minus 4.646. Okay. Okay. So you need another snip of Page 10. Okay. That's all we want to do for today. Well, that's quite a bit. We defined the Z transform. We found out it's very similar to Laplace transform. We defined some properties of the Z transform, like you could bring the constant out of the bracket. The sum of the Z transforms of two different time waveforms is equal to the sum of the individual Z transforms. We know that. Okay. We know that if we delay a voltage, we delay a signal, we have to multiply the original Z transform by Z to the negative K, where K is the amount of delay. We know how to get the transfer function of a filter, and we know how to find the poles and the zeros of that filter. We did all that today. Okay. I think I'm going to give you Monday's class off to study. So I will see you on Wednesday.
Yes, sir. See you later, Carter. Enjoy your weekend.
Yeah, you too.